Hello, everyone. I'm Ayanthi from the University of Ruhuna. I'll be presenting my work on text-to-face generation with StyleGAN2. So this is the outline for the presentation. First, I'll give you a brief understanding onto the background of image generation, and then present you the work that was done, and finally the results we have obtained. So before talking about text to image generation, we really need to know about image generation. And nowadays, generative adversarial networks or GANs, they are a very popular kind of networks that are used for image generation. They were introduced back in 2014, and here in the image is the diagram of a vanilla GAN, the architecture. So what happens here is there are two networks, a generator and a discriminator. The generator is responsible for taking in a latent sample, a noise sample related to the training data distribution and generating new data. And the discriminator takes in these fake generated images plus the real images coming from the data set and differentiates between them. So at the beginning, the generator performs very poorly and it will generate images that will easily be identified by the discriminator as fake. But over time, the generator gets better and it's capable of fooling the discriminator into thinking the generated images are coming from the real training data set. So they have performed really well, but there is one main problem with these networks. That is, we cannot request the generation of a particular image. Like for instance, if we are training this network on the MNIST data set, we are training the network to generate images of numbers. But we cannot use this network to request it to generate an image of number 8 for us. As a solution to this, conditional GANs were introduced. And here, in addition to the latent sample, we also introduce a conditioning variable. It could be a class label or something, some conditioning information, and that eliminates the problem, the said problem, and we can use this to request the required image. So they are very popular networks nowadays, and we see applications in image synthesis, style transferring, and so many other applications. Text to image generation that my paper focuses on is also another application of generative adversarial networks. Here, text is the conditioning information, and we try to generate an image to represent the content of the description. So the work that has been done so far is mostly based on birds, images of birds and flowers because of the complexity of the task. As you can see, if we look at an image usually contains much more data than what we describe in a description. Well, this is the main reason why this becomes a complex task and not much work has been done on this. When we are generating images based on a text description, we need to focus on two important measures, the image quality and the semantic alignment. Image quality means how far the generated images are realistic, and semantic alignment means how far the generated images are representing the content of our description, or how well the images are aligned with the description. And we see lots of applications for text-to-image generation as well, like in image processing, computer-aided designing, and even in game development. Text-to-face generation is a subcategory coming under text-to-image generation, where we focus on generating facial images based on a description. So the description will contain face attributes. We try to generate a face to represent those facial attributes. Now, unlike the descriptions about birds and flowers, these descriptions are very complex because facial attributes, they have a wide variety. For instance, if we take the ethnicity or the age group, there are so many variations that is there. So capturing them inside the image is really challenging. However, we see a number of important applications we can use this for. Especially if we look at public safety and criminal investigation. We know in police stations there is a sketch artist who makes a sketch of the criminal as we describe it to him. So if we can make realistic faces out of these models, we can use this to generate an image of the criminal instead of a sketch, and that would really help to make it easy for the investigation. And also when it comes to biometric research work that includes face data, like face detection or age estimation, we require a lot of facial images. And the data sets that we have at present, they are usually prepared by scrapping images from the internet and sometimes without even the owner's consent. So there are ethical issues related to this. And also when we look at facial data sets, there are racial biases like minorities not being represented. But if we can generate synthetic data that are so close to real images, then we can also address these issues. Because of the complexity of this task, not much work has been done in this field much. Um, yeah, so now let's look at the work that's been done so far. When looking at the literature, we focused on three main streams: text to image generation, text to face generation, and face generation. When going through the literature, we identified some key points. One point was the generation of low resolution images. Most of these networks, they went up to 256 by 256 resolution images, and they had hierarchical architectures. But using hierarchical architectures to improve the resolution of images is it's difficult and it's very expensive. So we need alternative methods to reach higher quality in the image. And also, looking at the text-to-face models, they were mostly built on top of text-to-image generation models. And then when we look at the language models that they have used, we noticed that most of the work they use word-to-word called graph embeddings with bidirectional STMs or skip thought vectors. But at present, we get better language models like BERT, and the use of these models in text-to-face generation has not been explored properly. Another thing we identified was there are high resolution face generators that are already available, like the StyleGAN2, but and they have the ability to generate images that are much better than the images that are generated through text-to-face models. But the use of these in text-to-face generation has not been explored much. So these were the key points that we identified when going through the literature. So based on these things, these were the questions that we tried to address. First thing was how to utilize high-resolution face generators like StyleGAN2 in text-to-face generation to improve the image quality. And in such a case, how can the semantic alignment be achieved? And also, how can the semantic consistency of the real and generated images be measured? So the overall objective of conducting this research was to develop a novel framework for text-to-face generation to generate high-quality images with semantic alignment. So we broke this down into further three specific objectives as to explore the possibility and ways of utilizing the StyleGAN2 generator for text-to-face generation and improve image quality, generate images that are semantically consistent with their input descriptions, and to measure this consistency. So now let's look at the methodology we proposed. Now, like when I was describing the architecture of a generative adversarial network, I said there is a latent space or latent space from which it samples some noise as input to the generator to generate images. So, so different points on the latent space will correspond to different images. So what we were basically trying to do was to find a way of representing text in the latent space, or in other words, to find how text and the latent space can be related. Like for instance, here, this description contains straight black hair. So we know this should be mapped to some different point on the latent space to generate this image. And the same description, if we change the straight to wavy, it will be mapped to some other different point on the latent space. So finding this representation was the overall idea of this research. In order to do this, we chose the text-to-face dataset. This dataset is a image and a dataset containing celebrity images and descriptions for them that was introduced with the text-to-face GAN paper. And a dataset containing celebrity images, they have been labeled using the shown attributes here. So in the text-to-face dataset, we get those images and these attributes being put into the form of a description. So here I've shown you two examples of from the text-to-face dataset. So in this dataset, there are around 192,000 data records, but because of the limited resources we had to limit it to, we chose 6,000 image description pairs for the training and evaluation processes. Right, so now let's look at the architecture of our proposed model. So if I tell, so you can see there are several models: the text encoder, the text to latent model, the StyleGAN generator, and the perceptual loss model. If we look at this on a high level, what we are trying to do here is to taking the sentence or the description, map it to a vector representation, and learn how to represent this in the the latent space using the text to latent model. Input that to the StyleGAN2 generator to generate an image. And the text to latent model is trained based on the perceptual loss calculated using the real image corresponding to the input description and the generated image. So now let's look at each of these components a little deeply. So for the text encoder, we chose BERT, which is a very popular model for its performance in NLP tasks. So the reason why we need a text encoder is we have a text description. We need to extract a vector representation of the text description to bring the text and image space to some common ground. So we use the text encoder here, BERT in this case, to obtain a 768 dimensional vector, or we call it the sentence embedding. In BERT, how these sentence embeddings are calculated is shown here. It takes the word embeddings and calculates an average of those word embeddings to get a sentence embedding. Because we only need the BERT model to obtain the sentence embeddings, we really don't have to deep dive into the BERT model. So we chose BERT as a service facility. It's a library that allows us to choose a BERT model of our choice and make inferences through it on our local machines. So we use BERT as a service to extract the semantic vector representation of the text description. The main reasons as to why we chose BERT, first, it's state-of-the-art performance in many NLP tasks, and it's a context-based language model that also follows bidirectional training, and for these reasons it has a very good performance in NLP tasks, and most of the work that is done on text-to-image and text-to-face generation has not explored the use of this model, so we focused on using BERT as our text encoder. So now we pass this to the text encoder and obtain a sentence embedding. And in the text to latent model, it's a simple multi-layer perceptual model. What we are actually trying to do is to learn how to represent the text in the input latent space of the generator. So here what we're actually doing is to map the text to match the dimensionality of its latent space. So then the output of the text to latent model could be input to the StyleGAN2 generator. The StyleGAN2 generator again is a very special model because unlike traditional generators, StyleGAN2 follows a very different architecture, and with that architecture, it has been able to generate images that are of high quality that can even fool humans into thinking the generated images are real images. The specialty of the StyleGAN2 network is here it has two latent spaces. Unlike the traditional network where there was only one latent space, here we have two latent spaces, the initial and the intermediate latent space. And there's a separate mapping network and the synthesis network. So the properties of these initial latent space and the intermediate latent space are different. In the intermediate latent space, the facial attributes, they are much more disentangled. So it has a better control over the style features like the hair or placement of freckles on the face. These things could be noticed in the intermediate latent space. With these reasons, StyleGAN2 is producing very high quality images, and we wanted to explore how we can use this in text-to-face generation. So once we input the latent sample to the StyleGAN2 generator, we can generate an image. And to further train the text latent model, we chose the perceptual loss. In perceptual loss, we know it compares the activations extracted through or the features extracted through different layers of the VGG16 model to bring them to or to make them similar. So now we chose the VGG16 model here. The layers that are closer to the input, they extract the filters, they extract features that are more closer to the input, like shown here. And as you go down the model, the layers that are closer to the output, they extract very coarse or very general features. So as we are trying to generate or make the image more closer to the real image, we need a balance of the initial layers and the final layers. And again, we chose VGG16 because we could also use models like VGG19, but with the limited resources, and because VGG16 is a simpler model, we chose VGG16 for our perceptual loss. So we try to minimize the perceptual loss and train the text latent model to bring the generated image close to the real image. So that was the architecture we followed here. And now let's look at how these images were evaluated. We need to evaluate both the image quality and the semantic alignment, like I said before. So to measure the image quality, we used the fit score, which again is a very popular GAN evaluation metric. It measures the distance between the feature vectors of the real and generated images by calculating the mean and covariance of the activations extracted through a model like Inception V3. And the lower the fit score, the better the images are, the more realistic the images are. And to measure the semantic alignment, we chose the face semantic distance and face semantic similarity measures. Now, like as I said before, semantic alignment actually means how far the generated images are representing the attributes of the input description. So the most natural way of thinking that the attributes in the description are represented in our image is to make a comparison between the real image and its generated image. So here in face semantic distance, we measure the distance between the activations, and the in semantic similarity, we measure the cosine similarity between the activations. So the lower the face semantic distance and higher the face semantic similarity, the better the images are. So now let's look at the experiments and the results we obtained. Um, when talking about the StyleGAN2 architecture, I said there are two latent spaces, the initial latent space and the intermediate latent space. So we needed to select which latent space suited best for a model. So we that was one experiment we did, and the other one was to select the most suitable feature map to optimize the perceptual loss function. So in order to do this, we designed two sets of experiments in the initial latent space and the intermediate latent space. So if we look at the experiments in the initial latent space, is that we conducted 3 experiments, and in the first experiment, we could not generate a realistic image. It just showed the structure of the face, and we assumed it was because of the perceptual loss function. So we improved the number of layers we selected, but still we could not achieve a good result. And then we focused on hypercolumns. A hypercolumn of a pixel is defined as the summation of all the activations above that pixel, activations of all the layers above the pixel. So it brings about the goodness of both the features that are fine details close to the image, as well as general features that are away from the image. But even with the use of hypercolumns, this was the best image we could generate. And the worst part of everything was that all these images looked alike, however much we changed the descriptions. As if the model could not really differentiate between the different facial attributes in the description. So we halted the experiments in the initial latent space and moved to the intermediate latent space. The most important thing we noticed here was in the first experiment, although it was not at all realistic, there was some sensitivity of the model shown to the facial attributes. And that was something that was that we were expecting to see. We could see the model being able to differentiate between the different attributes. So we conducted 3 experiments there, and these were the results we could obtain. So if I summarize all the experimental results, you could see in the first 3 experiments, although with different facial descriptions, the images generated looked alike. However, in the experiments 4, 5, and 6, it performed better. And when looking at the results from experiments 4, 5, and 6, on visual inspection, we selected experiment 5 to perform best among all the experiments. Then when looking at this in a quantitative aspect, we calculated the semantic distance, semantic similarity, and the fit score of all these 3 experiments. And experiment 5 performed the best. It reported a fit score of 118 and a face semantic similarity of 57% to the real images and a semantic distance of 0.92. So we selected experiment 5 as the best, and that was the model, the text-to-face model that we finalized with. So these are some of the example images that we generated using the experiment 5 and their related descriptions. We can see almost all these facial attributes are represented in these images. And now this is a small video showing how the images got better over the training process. At the beginning, the images were very vague, all features looked alike, but with time over training, they have learned specific attributes and the images are getting better over the training process. So now let's look at the validation and evaluation of the results. We evaluated these both on a qualitative and a quantitative aspect for both image quality and the semantic alignment. Here we have shown some of the images that we were able to generate on different descriptions using our model. We could see the face attributes are rendered properly, and there is some diversity among the images. And if we look at the semantic alignment, I said we could go only up to 57% similarity. So when comparing the real image and its generated image, they are not very similar, but we can see the facial features of these images are represented in our generated images. That means that the facial attributes in our descriptions have been represented in the generated image to a greater extent. Another interesting observation we made here was how sensitive our model was to the facial attributes. For instance, if we change the hair color or if we say no bangs, we could see those changes being made on the images, and that shows that in a way shows the semantic alignment of the images generated through our model. And then looking at the results in a quantitative aspect, we compared this with the other state-of-the-art models. Our model, we generated images of 1024 by 1024 in resolution, unlike the other images. And we achieved a fit score of 118.097, but because of the changes in resolution, we cannot directly compare the fit scores. And the face semantic similarity, we could go up to almost 57%, which is close to the face semantic similarity of other models, and low for semantic distance of 0.92. So the overall objective of the research was to develop a framework for text-to-face generation. So we wanted to use StyleGAN2, and we were able to improve the image quality. We used the BERT language model and also improved the alignment of the images with their descriptions. And we could go up to 57% similarity with their ground truth images. But however, there is still more room for improvement, especially if we look at the images, appearance enhancing attributes like earrings or necklaces, hats. These things are not shown in our images, and we need to focus on that. And another interesting direction is we were able to only generate one image per description. But when we look at a description, there should be more images that we can generate, because obviously for a particular description, there are so many other different faces that we can generate. So we need to work on the diversity of the images generated as well. And these are some of the references that we used in the presentation here today. And with that, I come to the end of the presentation. Thank you.